Our goal is to check the divergence or convergence of the following series, the summation of ln of n divided by n. Remember that you can always use the method of integral test, which basically says as long as you have a positive continuous decreasing function, then the integral of ln of x divided by x dx, x starts from 1 to infinity, gives you the convergence and divergence that you're looking for. But sometimes it's easier to apply other methods, like comparison test. In the comparison test, by looking at the series, if you can find a simpler series that you already know how it behaves, then you can apply that comparing two series. For the comparison test, we have two cases, two scenarios. Case 1 is when an is less than equals to bn, and then the larger series is convergent, and then you can conclude that the smaller series is convergent as well. Case 2 is when an is less than equals to bn and the summation of an, the smaller series, is a divergent series, and you can conclude that the larger series is divergent. So let us take a look at this series. I see ln of n divided by n. Why it is familiar to me? Because we already know the behavior of harmonic series. We already saw a different version of this series in the form of the summation of 1 over n. N starts from 1 to infinity, and as you remember, this guy is called the harmonic series. As a p-series, this harmonic series is divergent. The summation of 1 divided by n to power p, n starts from 1 to infinity. Since p is equal to 1, you get a divergent p-series. So how is it helpful to me? You're going to say that since 1 over n is less than equals to ln of n divided by n, so I can apply the comparison test. The smaller series, the series on the left-hand side, is a harmonic series. Is less than equals to the series of ln of n divided by n. So you can basically compare these two series. Since the harmonic series on the left is divergent, we conclude that the series, the summation of ln of n divided by n, also a divergent series. So let us recap what we did. We are checking the convergence and divergence of the following series. ln of n divided by n, n starts from 1, goes to infinity. You can apply integral test, check to see if the function is positive, continuous, decreasing, then take the integral. or you can use a simpler method, which is comparison test. Comparison test says you have two cases, two scenarios. If an is less than equals to bn, if the larger series is convergent, you can conclude that the smaller series also convergent. If the smaller series is divergent, you can conclude that the larger series is divergent as well. When we look at this series here, ln of n divided by n, we remind ourselves of harmonic series. Harmonic series was the summation of 1 divided by n is a special case of a p series when p is equal to 1, and we know that this is a divergent series. By using the integral test, you can check this as well. At the same time, since we already know the behavior of harmonic series, and we know that 1 over n is less than equals to ln of n over n, so since the smaller series, which is the harmonic series, is a divergent series, comparison test tells you, hey, the larger series must be divergent as well. It's not approaching any unique numerical value. It goes to infinity. You can also use the integral test. Let me quickly show you how to use integral test. We can also use the integral test. The integral of ln of x dx divided by x between 1 to infinity using a simple use of u is equal to ln of x, du is dx divided by x, which is already here, can be written as integral of u du, or a half u squared, or a half ln of x to power 2, x ranges between 1 to infinity. If you plug in infinity, ln of x goes to infinity. Since the integral is divergent, your series is divergent as well. Since the integral is divergent, our series ln of n divided by n starts from 1 to infinity, is also a divergent series. So sometimes the students feel comfortable using comparison tests. Some feel more comfortable using integral tests. So as long as you feel comfortable analyzing the behavior of a series, either method work, either integral test or comparison test.